Hi, my name is Rahul Chawla, and this is Lab 2, Motion of a Falling Object. A little introduction about the lab. So basically for this lab, we were tasked with determining the velocity and position of the same object falling in motion in different circumstances. So a big part of this was utilizing Newton's second law of motion, which I have written on the bottom of the slide, and the momentum principle, which is derived from Newton's second law of motion. Next, we had to record a video of a physical object falling in motion, so I chose a crumpled up paper ball. Then we programmed the computer model to predict the physical position and velocity of the object. And again, like I said earlier, we're comparing drag versus no drag, so those are two different scenarios for the same object. And then we compared both models to determine the effect on velocity, and we visualized the data in graphs for easy analysis. So I'm going to go into my tracker data now. So this is what I had to do. Basically, this is the object I chose, a paper ball, and I dropped it. And this is the data for that. Okay, so as we can see, the ball took around 2 seconds to fall completely, and we have a position versus time graph here in the top right where we can see how it's beginning to fall more quickly over time. That's because it's accelerating over time. And so now that we have seen the tracker data, I'm going to go into the data for the no drag model that I wrote with the VPython. Okay, so this basically briefly talking about the code. We have the mass for the ball, 0.0045. So I don't have a scale personally myself, but I went through multiple online sources that all sort of agree on this number for the weight of a paper crumpled up into a ball shape. So ball position initial condition vector, we have 0.893 and 0, so the only difference here is the 1.893 in the y direction, so that is the initial height that I dropped the ball at. That's basically my height with my arm extended out, dropping the ball determined by tracker. And then for ball velocity, of course, we have a 0 vector here because the ball is starting from rest. And then we have the givens, gravity is the acceleration, we have delta t for the time steps, j hat, the vector for the positive y-axis movement, and we have 0 proportionally constant because there's no drag. And then for the F net, since there's no drag, we only have one force on it, the F weight, which is basically calculated by ball mass times g times the j hat vector times -1 because we're moving in the negative y direction. And we have t here, and it's very important that t is a very small value here because that means that the position updates in smaller time steps, which means it's more accurate. And now I'm going to go ahead and run this program. So as we can see, the program is still running, and then position versus time, position seems to decrease exponentially, which means the ball is accelerating. The velocity is decreasing constantly over time, which means we have constant acceleration there with the force, and that's the first model. So now I'm going to go into the drag model. So basically the only thing I really had to change here, we have a lot of the same initial vectors. I just have a different proportionality constant, which I had to calculate by going over here. I found a formula to calculate the drag. So we have separate forces that are dependent on each different object that has different physical properties to determine the drag force. And for a spherical ball, we have 0.5 for the coefficient of drag. We have 0.04 meters for the reference area. The density of the fluid is air at around sea level, which is P, and the V is the average velocity over the time. And then using that, I was able to calculate the B constant. And then one more difference is we have two forces acting on it. Now we have the drag, which is basically just our proportionally constant times the velocity squared times j hat. And then I add those two together and I'll run the program. So as we can see, there's definitely a decrease in the velocity over time because the drag is acting on it, and the position is decreasing slower because we have multiple forces acting on the same object. So to sort of analyze it real quick, that's shown here. We see that the no drag actually followed the tracker model quite consistently, which is surprising because there was not that much error then in the physical representation versus the computer model, and the drag obviously fell a lot slower based on the data. For observations and comparison, we have the tracker fell to 0.09 meters, no drag model 0.1 meters, which is only 0.01 off from tracker, very close, and the drag model ended up at 0.55 meters. And these are the two graphs of position versus time and velocity versus time for the drag model and the no drag model. So you can see how we're approaching a terminal velocity here. Speaking of terminal velocity, that was one of the questions that we were asked to answer, and basically we were asked will there be a terminal velocity on the drag model eventually? And I think definitely there will be, because eventually the drag will increase to a point where it will balance out the force with the weight force, which will leave us with acceleration of 0, which will mean that the velocity will remain constant. And then another question we're asked to answer is, what if the ball was thrown directly downward? Would there still be a terminal velocity? I still think there would be, because the forces would still cancel out in the same way as I said earlier. We will be left with a net force of 0, which means acceleration is 0 and the velocity will remain constant. Thank you for watching.